Good afternoon. I'm Ethan Allen, and you've joined Likeable Science on ThinkTech Hawaii, broadcasting here from the studios in Pioneer Plaza. This is a streaming network series. Likeable Science is devoted to the idea that we should all recognize more that science is part of all of our lives and can be fun and enjoyable things to learn about. Today, to help me explore this area a little further, I have Dr. Leslie Au, who is a senior biomedical engineer at OceanIT, and our topic today is going to be bioengineering, medicine, and more. Welcome, Leslie.
Hi, thanks for having me.
Glad to have you here. So Leslie's actually an amazing person. She has, as I was looking at her resume, I found she has 2 bachelor's degrees, 2 BS degrees, one in biochemistry and chemistry with distinction, and simultaneously got a degree in molecular, cellular, and developmental biology, also with distinction. It was back in 2005. She got a master's in chemistry in 2007. I met her, I think, a year or 2 after that, right, Leslie? When she was in the starting up in the Center for Nanotechnology at the University of Washington, where she got an early bird award and later one of the very prestigious IGERT fellowships, Integrated Graduate Research Education and Training fellowships. Later on, she finished up her work at the Washington University in St. Louis in bioengineering department, with her dissertation being engineering the optical properties of gold nanostructure for biomedical applications. So quite a mouthful there. So Leslie, can you maybe tell us a little bit to start with about what OceanIT does and what kind of group it is?
Yeah, so OceanIT is a small privately owned company, and it's located here in downtown Honolulu, and we also have satellite offices on Kauai and Maui, and some little offices across the mainland continental US. And we do a very wide range of research, and it started out as a coastal engineering company, and so naturally it grew to environmental engineering, and then to science and technology, and that's the group I'm part of.
Huh, excellent. And so what does a biomedical engineer do in a general sense there at OceanIT?
Well, biomedical engineer can do, it's such a broad category. My background is actually in chemistry and biology. That's how I started. And then what I've done is I've worked with nanomaterials and using them for biological applications. And one of them is cancer therapy. So, but biomedical engineers could be someone who's trying to make a new robotic arm, or tissue engineering, making a new heart.
Excellent. So, can you tell me a little bit about what sort of drew you into science? Why did you get interested in science, and when did this happen? What were some of the people or events that got you interested?
Very early on, I knew I was just very curious, like most children are. They're very curious, but I always had to, kids ask why, and question things, and then want to prove it to themselves. So when someone said water boils at 100 degrees, I was like, oh, okay, I'm going to test this out. And so I would boil water, and I put a thermometer that wasn't made to go 100 degrees Celsius. It was, for body temperature. So I just dipped it in, and it went, boom, it just exploded. It was a glass thermometer that had mercury. So then I spent the rest of the afternoon, tracing after the mercury and cleaning up the mess. Yeah, so I was very interested in science from a very young age. And it wasn't until I took chemistry in high school when I felt like my answers, or the questions I had, were finally answered to the degree I wanted, which was like on the subatomic level, like to electrons and protons and how that worked.
Well, excellent. No, and good for your parents for encouraging your curiosity. It's all too easy to quash children's curiosity. It sounds like yours was indulged and allowed you to continue to have that, and that's really critical. And science has always come relatively easily to you then, in terms of understanding the concepts and growing your knowledge?
Yeah, math and science where it seemed more natural to me.
I tend to agree. I always found languages very tough because they seem to set up a structure like science, but then to break all their own rules. Whereas science rules are fairly consistent. Well, excellent. And so let's maybe dig a little bit more into the kinds of work you're doing at OceanIT here. You are studying a variety of different projects right now. The one that particularly intrigued me was you're doing a little work you said on a medical device for transcranial treatment of brain hemorrhage. So being able to treat a injury to the brain where you're getting bleeding underneath the skull without actually going through the skull, without drilling through the skull.
Right. Yeah. So one of the problems is when people get into concussions or into some blast injury for military purposes, they can break the epidural artery, causing a hematoma. And what that happens is the blood pools, and it causes the brain to kind of push in. And so after a certain pressure, the pressure in your skull, you'll have like irreversible damage and you'll die. So currently how they do it is what you said, is they drill a hole to release the blood from there. And our goal is to direct energy through the skull so you don't have to drill the hole, and to cause that artery to stop bleeding.
Oh, I see it. That's very intriguing. So to either pinch it off or clot it or in some way to stop it from dumping more blood in, thus just stop the increase in pressure. And then the rest of the existing blood will just drain out more or less by itself.
Yeah, your body naturally,
Right.
well, if it's a small amount, it can reabsorb some of the blood.
Okay, excellent. Well, that sounds very exciting, and immediately sort of in line with the theme of the show, you can see where this kind of science has tremendous application, right, to any sort of stroke, certain kinds of brain trauma could immediately help make people's lives a whole lot better, which is wonderful. That's why we do science, right? Mm-hmm. Excellent, excellent. And you do other sorts of biomedical related work here, I know. I see something here about you're working on a wound healing bandage using electrospinning techniques. Can you talk a little bit about what electrospinning techniques are and why this is useful in wound healing?
There's another person in our group that does electrospinning. So they use some gelatins and maybe hydrogels, which can absorb liquid very quickly, and this can help the clotting. You know, when you absorb liquid, it can help the clotting of a wound.
Oh, okay. What's this electrospinning business? This is what I.
So you can deposit very thin fibers and make a mat out of it. Yeah.
Okay, so that makes it sort of the bandage part. Mm-hmm. Oh, I see. Okay. Well, that sounds again like a potentially very useful sort of thing. If it's so its absorbency then is greater than that of a standard fiber or something, and therefore it works better for. Does it integrate better?
Well, we also add cytokines and some other factors to help the clotting process.
You can put materials into this hydrogel then, around the hydrogel, so it sort of adds to its usefulness. Mm-hmm. Excellent, excellent. Well, that all sounds good. So how did you get into this kind of work from your work on gold nanoparticles that you did as a graduate student? It seems like something of a jump here.
So when I was undergrad, I got involved in undergraduate research, and the professor who I was working for, Yunan Shah, he was one of the people who just started synthesizing nanostructures with controlled shape and sizes. So I got involved with that, and when I became a graduate student, I sort of we had a meeting together, and he asked me, or we had a meeting to talk about the next 4 years of my graduate study. And he said, with a last name like mine, AU, which is the atomic symbol of gold, he said I had to work with gold. So the next 4 years I was working with gold. And so we were synthesizing gold nanostructures for bio applications.
Excellent. And the whole business of the nanoscale and building structures at the nanoscale, that's amazingly small, right? A nanometer is a billionth of a meter, or about the amount your fingernail grows in 1 second, right? Which is not much at all. Mm-hmm. How do you maneuver, work with materials at that scale?
It's very sensitive. I remember if your glassware is dirty, the reaction didn't work. So, yeah, so it was a lot of mixing of solutions, and then after you carefully do that, you would image your structure using an electron microscope. So.
Yes. Okay. Right. Either a scanning electron microscope or a transmission or a atomic force microscope, depending upon sort of what you were building there. So you would mix different kinds of solutions, put them on different substrates, and build it. So, so how does that then tie on into this sort of this current work? You're using some of the same techniques, or?
So I was using gold nanostructures for cancer applications, and when I was hired here at OceanIT, I was transitioning from gold nanostructures to carbon nanotubes for cancer therapy.
So I've heard a lot about carbon nanotubes in terms of they're very useful materials in a lot of different applications. Very strong, lightweight. How do you buy these commercially? Do you make them yourselves?
We can make them. Yeah, we can make them. But for the bio application, we did buy them commercially.
And if you can you tell us sort of briefly how you go about like making such things if you were trying to do that?
Well, in carbon nanotubes we purchased, but then after we purchased it, there's still some processing we have to do to clean out any other amorphous carbon that's on it, and then we would attach biomolecules onto it so it can recognize the cancer cells. So we would attach antibodies.
Okay, and that must be a fairly technically challenging process, I would guess.
Yeah.
Because you have to attach just the right molecules in sort of just the right concentration in just the right way. Is this more of a sort of mechanical process, or again, do you use sort of take chemistry and put it to work for you?
Yeah, this is chemistry. We use we covalently link them together. Yeah.
Okay, so they're actually bonded then to the carbon nanotubes. Mm-hmm. Excellent, excellent. So again, you've got this same idea that you've got structures at a tiny scale, at a scale of a few nanometers or a few tens of nanometers that have then both the right shape, sizes, electric charges to carry out the particular task that you want to do, right?
Right. So what we wanted to do is we wanted to attach chemotherapeutic drugs to it and make sure that it would deliver that just to the cancer cell, not throughout the body.
Well, good. Now I understand sometimes gold nanoparticles themselves without any adornments have been used to treat some cancers. Is this, do I understand that correctly?
Yeah.
And how does that work?
So gold nanostructures, they have, as well as carbon nanotubes, they have the ability to absorb infrared light if you tailor its optical properties. And then when they absorb infrared light, it vibrates and it causes heat. And then if it's attached to, or if it's near cancer cells, it will cause the surrounding area to heat up. And so you can kill cancer cells via hyperthermia.
Excellent. So we'll be taking a small break here. I'm Ethan Allen. I'm here with Dr. Leslie Au. We're talking about bioengineering, medicine, and more. We'll be back shortly.
Aloha. I'm Nicole Horry with the ThinkTech Commentary. The PUC has established an investigative docket to determine the advisability of an undersea cable connecting the Oahu and Maui electrical grids. It has scheduled public meetings on both Oahu and Maui to invite comments on the proposal. The PUC is investigating whether a transmission cable between the two islands is in the public interest and whether the benefits to ratepayers would exceed the costs of the cable, which DBET estimates would be $700 million. The PUC also wants to know about development risks and how they would be mitigated. With the remarkable increase in PV in the islands and the availability of new grid technologies, it may be possible for each island to generate renewables that meet its own demand and to have separate renewable grids for each island instead. At the same time, an island that depends heavily on a source of renewables, such as PV, may be vulnerable to local changes in the weather or an unanticipated problem with that single method of energy generation. The ultimate question for the PUC, then, is not simply whether an undersea cable is good for Hawaii, but how we can achieve layered redundancy for a resilient statewide system. ThinkTech believes that a great state needs ample power distribution, and that the proper approach is to start with this undersea cable, not only to bring the separate island grids and the state together, but as part of a strategy to achieve the security and safety of redundant systems. I'm Nicole Horry with this ThinkTech Commentary. Mahalo.
And we're back. I'm Ethan Allen, here on Likeable Science on ThinkTech Hawaii. My guest today is Dr. Leslie Au, a senior biomedical engineer with OceanIT, and we are talking about bioengineering, medicine, and more today. So, Leslie, I understand that some of your work gets a little bit away from the biomedical field exactly, and is concerned with actually, instead of making something sort of more visible, more easy to see, is quite the opposite. It's trying to hide things. Can you talk a little bit about this work?
Yeah, sure. So this, it's an Obscurant project that I'm working on, where currently our military forces, the way they are not seen by the enemies is they use smoke. Currently they use smoke. But now the enemies are able to have detectors that can see beyond the smoke, so see beyond visible, and they can see more the infrared or heat signature of people or tanks. So the goal here is to develop a new material using nanostructures to try to block the heat signature so they can't see in the infrared region.
Now, would this be something that will go into the smoke, or would it go over the people, or?
It would be like a cloud, like an aerosolized cloud.
Okay. And so it would just, again, you'd be designing in the same way as your other work. You'd be designing a material that has particular, in this case, sort of physical properties that makes it opaque to infrared radiation. Mm-hmm. So you can't use your night vision goggles and see through it or whatever.
Right.
Oh, excellent, excellent. Well, that sounds like, again, another very interesting and useful application. It seems like there might be even more, perhaps other non-warfare applications for this too. The issue of trying to hide things, of course, and make invisibility, well, I want to say cloaks, as it were, from the science fiction literature, is of course a very hot area now. I gather there's other work going on with actually really actually bending light around objects on using what are called metamaterials. Mm-hmm. So do you do any of that, or is that
I don't do the metamaterials, but there are some people in our group that are working on such things. So
I've never really understood exactly how those work. What's the underlying principle? Can you explain that at all?
No.
I know they do. They bend light somehow and then sort of recorrect it, so you never see that it would bend out of a pathway. Okay.
They have a different, like a negative index of refraction to do that.
Which has always puzzled me. But so, and Alyssa, again, you do so many different kinds of things here. I see, and I know you had one project I just wanted to touch on briefly here. You at one point worked with a troop of Girl Scouts who were getting a project to put up on the space station.
Yeah, they were trying to germinate some seeds up in space, and then to see what kind of wavelengths of light, red light or blue light, would help them grow better. And this is more for, this was sort of a sustainability, like growing plants up there for astronauts.
I see. Okay, so that sounds like maybe a little more distantly related to your work in that sense.
Mm-hmm.
Okay. So, can you talk a little bit maybe about some of the challenges that this work has had for you? Have you? I know, for instance, some of the engineering fields have very, what can we say? They are very unbalanced gender-wise, with computer science, for instance, being very heavily dominated by men with relatively few women in the field. Is that less true in bioengineering?
Yeah, in biomedical engineering, there's probably 50-50 male and female.
I just saw recently that, it surprised me that women are now getting more than half of the doctorates in the U.S. and actually have been for about the last decade, just by a small margin. I was sort of amazed. I'd always thought that it had been, and I guess it had been in prior years the other way, but no, so that's wonderful. That's wonderful, and it's great that you're doing work then to help encourage young women to pursue STEM studies and all. That's top notch. But you say you yourself haven't really, you don't feel like you've been limited or subjected to gender bias or anything in your studies or your career at all.
Right, yeah, no, I haven't.
That's great to hear. We hear, unfortunately, all too much of that, and even in the field of science, there's been some recent revelations that it's all too common, and so it's good to hear that at least it's not totally pervasive. So maybe we can look a little bit at the some of the broader applications of this work. Do you see this stuff sort of where do you see it going?
The field of biomedical engineering?
Right, in a broad sense, yes. I mean, is it helping us? Well, it's clearly helping in the biomedical field. Other areas?
Well, I think we're going to be doing more amazing things, like with these robotic limbs and even tissue genesis. Yeah.
Yeah, I've been reading about both of those ideas a little bit here. That the more and more the controlling devices, actually limbs, in some cases remotely, has really been booming recently. Mm-hmm. I was seeing a piece recently on learning what the scientists took a small independent drone, as it were, a little helicopter, put a skull cap with electrodes and had people just envision clenching and unclenching their fists by way of controlling it. And they apparently within a few moments, most people could learn to control this device and fly it around three-dimensional space and run it through simple mazes. Mm-hmm. Stunning that we can have that level, and once we have that, of course, it does seem it opens up large doors, particularly to people with disabilities of various sorts, but for all of us to really extend our reach, as it were. And you were saying about the tissue generation. This is just like the work on growing organs now.
Yeah, growing organs or skin. Mm-hmm. Yeah. It's amazing, and as that, I think, as it ties in more with some of the work that you're doing, I mean, we should be able to
grow tissues with sort of enhanced functionality, as it were, right? Even sort of better than nature in some sense, potentially that either is stronger or responds more positively to certain stresses or whatever. So some tremendous opportunities there. Excellent. Outside of biomedicine, it seems there's got to be other things too. I know material scientists are constantly sort of in the same realm of building material up from molecular level with desired properties, somewhat like your obscurant material you were saying, but in a whole wide range of other applications too, adhesives and building materials. I mean, I gather that doing nanotechnologists are getting into making concrete now, which seems, I mean, there was something that was made by the Romans, right? And now the nanotechnologists are getting their hands on it, and making self-healing materials.
Right. So,
really very, very powerful sorts of applications, I think. So that it would appear they're going to have wide-ranging impacts on our lives in the future.
Right. Yeah. From like you said, from concretes to the bio application.
And of course, they've already having such impacts on the computers, making computer technology more and more pervasive, getting all the computer components smaller, enabling us to, we all now carry around in our pockets what we call a cell phone, but it's really an amazingly multifunctional computing device, right? That can do 1,000 tasks, most of which I have no clue about. Yeah, where is it all going to go? So, can you tell us a little bit, maybe more about other work at OceanIT? Are there other sorts of projects happening there that the world ought to know about?
Yeah, there's a lot of materials chemistry that we're doing. So like you were saying, we also have made some nano concrete where they put where they have carbon nanotubes incorporated in the concrete, so they can help sense like help sense like whether you have like cracking in there and such.
And I've heard about the idea of making materials like that, which even after they crack, they will then sort of seal their own cracks. I'm puzzled as to how you build materials that sort of know that they've broken and then are able to repair that themselves without external agencies.
Yeah, so you were saying about the self-healing paints. I've seen some of that work where they need an external agent where they use heating and such.
Oh,
yeah.
Okay.
But yeah, the other one.
No, that would seem that kind of stuff might be useful here on we've just been reading all about the troubles on the North Shore with the large waves breaking down seawalls and all. If you had your seawall with your smart concrete, as it were, it could at least tell you when it was getting ready to give, right? And you could then take appropriate action. So that would be certainly another useful thing to know. Anyhow, I think we're about at break time again here. So again, you're listening to Likeable Science. Ethan Allen here. We're on Think Tech Hawaii. My guest today is Dr. Leslie Au. We're talking about bioengineering, medicine, and more. We'll be right back.
Aloha. I'm Nicole Horry with the Think Tech Commentary. The PUC has established an investigative docket to determine the advisability of an undersea cable connecting the Oahu and Maui electrical grids. It has scheduled public meetings on both Oahu and Maui to invite comments on the proposal. The PUC is investigating whether a transmission cable between the two islands is in the public interest and whether the benefits to ratepayers would exceed the costs of the cable, which DBET estimates would be $700 million. The PUC also wants to know about development risks and how they would be mitigated. With the remarkable increase in PV in the islands and the availability of new grid technologies, it may be possible for each island to generate renewables that meet its own demand, and to have separate renewable grids for each island instead. At the same time, an island that depends heavily on a source of renewables, such as PV, may be vulnerable to local changes in the weather or an unanticipated problem with that single method of energy generation. The ultimate question for the PUC, then, is not simply whether an undersea cable is good for Hawaii, but how we can achieve layered redundancy for a resilient statewide system. ThinkTech believes that a great state needs ample power distribution, and that the proper approach is to start with this undersea cable, not only to bring the separate island grids and the state together, but as part of a strategy to achieve the security and safety of redundant systems. I'm Nicole Horry with this ThinkTech commentary. Mahalo.
And we're back. I'm Ethan Allen, and you've joined us on the Likeable Science here on ThinkTech Hawaii, broadcasting from the ThinkTech studios in Pioneer Plaza. My guest on Likeable Science today is Dr. Leslie Au, a senior biomedical engineer with OceanIT. And Leslie and I have been talking about bioengineering, medicine, and more. So Leslie, your graduate work dealt with building small gold nanocages, you call them. Mm-hmm. And I'd love to look a little more deeply into this. What was the reasoning to build these, and what were you doing with them?
The first thing we were studying was how to control the shape of them, and then from there we learned that these shapes and different sizes have different optical properties. For instance, when you think of gold, you think of this yellow, shiny material, but when you miniaturize it into the nano size, they have different colors. Like they can be red or blue in solution. So how I made the nano cage was I started off with a silver nanocube. And then from there, I was able to drip gold solution in there, and what that did was it caused, there was a galvanic replacement reaction where the gold was able to turn into, the gold ion was able to turn into gold, and then the silver kind of leached out as ions. So we were able to control the optical properties so that it could absorb in the visible region to the near-infrared region. And what we want to do is we want to focus on the near-infrared region because biological tissues, they are transparent in that region, meaning the gold nanocages, they can absorb light in that region and not the tissue.
And this then gets back to the issue we spoke of earlier about the using gold nanoparticles for cancer treatment, and has to do with their size, both impacting how they absorb infrared radiation, but also it has to do with the biological properties, right? Because they would essentially leak out of your capillaries into tumors, where the blood vessels are slightly further apart than they are in the rest of in healthy tissue. Is that sort of the case? Right. So they gradually accumulate supposedly in your tumors. If you then shine this infrared radiation on there, the gold nanoparticles pick this stuff up that's passing harmlessly through tissue and then re-emit it as heat, killing the tumor. Oh, excellent, excellent. So that's fascinating how the moving things to a nanoscale, you're able to tune properties in that way for both of the sort of the physical properties and the chemical properties both. Mm-hmm. And quite intriguing. But you sort of gave a very facile answer there about forming the gold nanocages from silver nanoparticles. So I mean, it begs a question. It's like the turtle standing on top of the turtle on top of the turtle, like for making the Earth. You know, how did you get the silver nanoparticles?
The silver nanoparticles. You started off with silver ions in solution, and there's different facets to these silver nanoparticles, and we can use polymers to sort of cap certain facets so it can grow into the shape you want.
So you attach these polymers onto sides or ends, and then they grow the other ways, or?
Yeah, they grow, like if you start, yeah, they grow more into the corners, say. So if it starts with a sphere, you cap, there's polymers that can cap the 100 facets of the cubes, and of the sphere, and then it grows on the 1-on-1, which makes it into a cube.
It's really stunning that we've gotten that level of fine control over the building blocks of materials, really, and it does sort of say we're moving into a very new realm of engineering here.
Right. Yeah. Before it was more of an art, and now now that we've done it enough times, it's more of a science.
Well, too, you're getting into this whole issue now. Much engineering used to be sort of a top-down process, right? You take a given material and you sort of mill it away or hammer it or whatever and push it into the shape you want. And now you can actually grow it from the atomic level up with exactly the desired properties that you want. And of course, now this sort of ties in, I guess, to the 3D printing that's becoming increasingly popular, right? Where you have printers that can take a given material and form it build it up layer by layer very quickly into your whatever shape you desire. I guess that's become now just absolute routine where they can do that.
Right.
And of course, that opens up all kinds of potentially great options, but it also opens up some fairly unfortunate problems, right? The whole new issue of plastic weapons.
Oh yes, yeah.
Where we're facing a real struggle, I guess, to figure out how to control that, and the solutions are not yet clear. One idea, of course, is to put metal particles in with the plastics, right, that are sold for that application, so that all the plastics will have a certain amount of metal in them, and thus will show up on X-rays or whatever. Mm-hmm. But one senses that's probably not the ultimate solution to this kind of problem, is it?
Yeah.
Yeah. So going back to these gold nanoparticles, and you spoke of the ability of the different ones to be different sizes. They would turn different colors in solution. And I recall seeing, I was actually some of your colleagues, I think, on the same idea, except with silver, doing silver nanoparticles of different sizes and making different colors, and trying to find a relatively simple recipe to do that, to illustrate, because it's a core property of nanotechnology, right? Is that you have these properties that emerge on the nanoscale that don't that don't appear.
So this property is called localized surface plasmon resonance. Yeah.
That's a mouthful.
So yeah, it's the conductive electrons of a metal. They'll like oscillate at a certain frequency, and that causes these colored properties, optical properties.
And because when you're dealing at the nanoscale with the individual particles, you then have a much higher surface to volume ratio, right? For each particle, and therefore this property becomes sort of more and more important, where it wouldn't be important in a large chunk of metal, because there's actually relatively little surface to a lot of volume, but in a tiny particle there's a tremendous amount of surface relative to the volume.
Right.
Oh, okay. Well, that's see, you get back to mathematics here, right? You know, the whole figuring out the mathematical laws of surface area relative to volume on a given shape. It gets, so when did all this? How did all this get started? Do you know the sort of the driving force behind all this sort of nanoscience, nanoscale science? I mean, Richard Feynman is often credited with sort of opening up that whole Pandora's box, right?
Yeah, there's plenty of room at the bottom.
Right? It's a very, very famous talk, right?
Yeah. I want to say it started with electronics, when they were trying to make components in the computer smaller and smaller to store more data and such.
Yes, because of course that then both makes them less expensive. You can get more bang for your buck, more information, less space. You have less heat trouble. Yeah, it's quite stunning now that the smaller computers we have now don't seem to get nearly as hot as the bigger, older machines that we used to have, right? They don't, yeah. And that was, of course, yeah, I can see that would be a driving force because there's a huge market for that kind of thing, and selling billions and billions of these integrated circuit chips. That's certainly going to drive the drive the whole field. Other potential applications. I know there was some intriguing work going on. Maybe you've looked at a little bit of this with the whole issue of adhesion. The question has always come: how do you, for instance, in biomedicine, wouldn't it be nice to be able to sort of glue wet tissue together and have it stick? And of course, the classic are the mussels on the rocks, who are able to stick themselves very firmly to wet rocks, to dry rocks, and have these byssal threads that are tremendously adhesive under a wide variety of conditions. And again, then that would open up possibilities for repairing a boat in process, in transit if it springs a leak. Is this again sort of the same issues of looking at the molecular structure, the atomic structure, and building something that has just the right kinds of properties? Is it, I mean, on that level, it's...
Yeah, I remember when I first started here at OceanIT, they were talking about this gecko project where they took a gecko's foot and they looked at it under the electron microscope. And if you look at it carefully, it almost looks like carbon nanotubes, where it's all there's these nice fine pads, and it's very thin fibers at the very end of their foot. And you wouldn't have known that if you didn't take a closer look at it. And we try to mimic biology and develop some using materials and try to develop materials for similar purposes. Yeah.
Excellent. Well, we're going to take another little break here. This is Dr. Leslie Au, Senior Biomedical Bioengineer at OceanIT, and I'm Ethan Allen, your host on Likeable Science. We'll be on break and we'll be right back.
Aloha, I'm Nicole Horry for ThinkTech. For nearly half a century, the Hawaii Foreign Trade Zone No. 9 has brought the benefits of the Foreign Trade Zone program to Hawaii businesses and entrepreneurs. DBET, the Department of Business, Economic Development and Tourism, operates Hawaii's Foreign Trade Zone program to encourage international business and economic development. The Foreign Trade Zone's mission is to increase the amount of international trading activity in Hawaii, thereby providing employment opportunities for the residents of our island state. For more information, see ftz9.org. I'm Nicole Horry. Mahalo.
And we're back here on Likeable Science on ThinkTech Hawaii, broadcasting from the ThinkTech studios in Pioneer Plaza. I'm your host, Ethan Allen, and my guest today is Dr. Leslie Au, a senior bioengineer at OceanIT. Leslie and I are talking about bioengineering, medicine, and more. And Leslie, you just brought up before the break the intriguing area of so-called biomimetics, of trying to learn from nature to see how nature is solving problems. You brought up the issue of gecko feet. And gecko feet, for our viewers who might not understand why they're so interesting, geckos are able, of course, to run upside down across ceilings, and their feet are simultaneously very sticky and yet also have the ability to be removed very easily by the gecko from the surface. A very intriguing blend of characteristics whose basis lies in its fundamentally sort of it's almost molecular level structure, right? Having these extremely long, fine nano hairs, as it were, right, which give tremendous surface area, so that they stick to the surface that the gecko is on, but at the same time the gecko can remove them one by one, as it were, except a million by a million, and thus move its feet at the same time. So I gather they're trying to make, was Ocean involved in this, trying to make tapes on the same? Did that pan out? Are those things around now, or?
Well, we have a demo where we have a little robot that can climb up along walls for that.
Cool. I understand they were actually looking at the same kind of thing to do that underwater too, to have a tape that would adhere underwater, which would again be a useful sort of thing. So there's all sorts of different ways that could be useful, from marine and ocean science work to, again, back to your biomedicine, to sticking band-aids on arteries, as it were, as it were. So that could be another area yet of research here. So it sounds like this whole field of bioengineering is really going off in a lot of different directions at this point, and having a wide-ranging impacts. So we can expect to see great things, and from I'm sure your work will contribute to this.
Yeah.
Well, excellent. Just to review, I mean, Leslie's work includes developing these so-called obscurant materials to help make personnel more invisible in military-type situations. She's also working on developing a medical device or medical treatment for a transcranial treatment of brain hemorrhage, so being able to treat hemorrhages without having to drill through the skull. She's working on targeting cancer using a carbon nanotube drug delivery platform. She's developing nanobiosensor arrays to check out for adverse drug reactions, and is also doing a wound healing bandage. So you can just see from Leslie's work alone some of the real breadth of the bioengineering field. Well, I thank you very much, Leslie, for coming on and sharing your work with us. It's certainly intriguing to learn more about your research and about the work of your colleagues there at OceanIT also. And it fits in well with the theme that we're trying to work on likable science here, in the term that we can see a lot of very clear impacts and implications and applications of this kind of work right away to a wide variety of life situations. We talked about sort of structural issues of building concrete, to fixing boats, to fixing arteries and healing diseases. Tremendous different possibilities out there, and it seems like it's a field that's in a very exciting phase right now. Do you have any sort of last words of advice to people sort of considering this as an area of study or a career?
Yeah, I mean, I enjoy it very much, and I didn't realize how diverse, and how many different types of things you can do with it. So part of what I do now is try to educate younger children and let them know, like, there's different types of engineers in addition to, when I was younger, I didn't realize that there were more than one type of engineer. So.
Right. Yeah, we all thought of just sort of standard civil engineers who built bridges, and now, yes, you have bioengineers, you have chemical engineers, you have electrical engineers. There are and people who cross those lines back and forth, as indeed some of your work seems like it does, really. So that's, and again, it all suggests the need or advisability for young people to get a good broad science education, right? To prepare themselves for this kind of exciting work in the future. Excellent. Well, I hope this has been as much fun for you as it has been for me. It's been truly great to see how your work has grown and changed from your graduate student days, but in a very sensible, logical way. And as I say, it really makes me feel good to see this kind of point that I was trying and that I was hoping would be made on the show, which is, yes, that there are lots of reasons to be interested in science. There's lots of intriguing stories here. There are lots of great applications of science to be had. And as I said, I do very much appreciate your coming on and sharing your work with me.
Well, thanks very much for having me here.
Well, thank you, Leslie, and aloha to you.